Imagine a machine that defies gravity, disappears from radar screens, and fights with the collective intelligence of a hive mind. Sounds like science fiction, doesn't it? Yet, this isn't a fantasy from a blockbuster movie. This is the F-35B Lightning II, arguably the most advanced aircraft ever conceived, a true marvel of modern engineering. It's a plane that promises to redefine air combat as we know it, blending the roles of multiple legendary aircraft into one incredible package. But how do you combine the agility of an F-16, the vertical prowess of an AV-8B Harrier, and the stealth of a B-2 bomber into a single airframe without making impossible sacrifices? The F-35B is designed to be a jack-of-all-trades, a stealth fighter capable of engaging both airborne and ground targets with unparalleled precision. It's built upon decades of lessons learned from Lockheed Martin's previous ventures into stealth technology, drawing heavily from the revolutionary F-22 Raptor and the iconic F-117 Nighthawk. But the F-35B doesn't just incorporate these capabilities, it dramatically improves upon them. It's fitted with the most advanced sensors and computer systems imaginable, allowing it to share information almost instantly with allied forces, all while maintaining its elusive stealth. This real-time data is presented directly on a heads-up display integrated into the pilot's helmet visor, offering an almost superhuman level of situational awareness. Can you even begin to comprehend the tactical advantage of effectively seeing through your own aircraft? This incredible fusion of technology allows a flight of F-35s to operate as a single, coordinated entity, a true hive mind in the skies. But perhaps the boldest, most audacious capability of the F-35B is its ability to transition from horizontal to vertical flight with a simple push of a button. Utilizing directional thrust and a massive internal vertical turbofan engine, it can hover and land like a helicopter. This feature is not just a party trick. It means the F-35B can operate from the relatively small amphibious assault ships of the US Marines, extending its reach and tactical flexibility exponentially. But how do engineers manage to cram all this cutting-edge technology and such conflicting requirements into a single, cohesive airframe without compromising performance? Designing for stealth is perhaps the ultimate compromise. It demands meticulous sculpting of the aircraft's exterior, dictating the shape of almost every crucial feature and creating a cascade of unavoidable trade-offs. There's a common misconception about what stealth truly means. The goal isn't to make an aircraft genuinely invisible. That's simply not possible. Any object, no matter how advanced, will eventually be detectable. Instead, the objective is to delay enemy detection for as long as humanly possible, ideally allowing the aircraft to complete its mission before it's even seen. So, if true invisibility is impossible, what exactly are we fighting against? For bomber aircraft, this delay in detection can dramatically shrink the effective range of enemy radar stations, potentially opening critical gaps in air defenses. This allows stealth bombers to slip through undetected to their targets. For fighter aircraft like the F-35B, stealth provides an even more critical advantage: the ability to detect your enemy long before they ever become aware of your presence. This first shot, first kill capability is paramount in modern aerial combat. To achieve these game-changing advantages, engineers must make it incredibly difficult for a radar receiver to differentiate between an actual enemy aircraft and mere background noise. This means minimizing the strength of the return radar signal. But how do you prevent radar waves from bouncing straight back to their source, effectively screaming, "Here I am"? There are several ways a radar wave can be reflected, but the most significant is specular return, or regular reflection, much like light bouncing off a mirror. Here, the angle of reflection precisely equals the angle of incidence. To minimize this, designers must avoid large, flat surfaces that could reflect radar waves directly back to the receiver. Even more critical is the avoidance of corner reflectors, where two surfaces meet at a 90-degree angle. These are absolute nightmares for stealth, as radar waves can bounce off both surfaces and return exactly in the direction they came from, creating an incredibly strong signature. Tailplanes, consisting of vertical and horizontal stabilizers, are notoriously problematic, as they naturally form perfect corner reflectors. So how does an aircraft maintain stability and control if you can't have traditional tail surfaces? The most straightforward, if impractical, solution to the corner reflector problem is to remove the tail completely, as famously seen on the B-2 Spirit bomber. While this dramatically reduces radar cross-section, it comes with a severe penalty: significantly reduced maneuverability, which is unacceptable for a fighter jet like the F-35. Instead, engineers opt for a more ingenious solution, replacing both the horizontal and vertical stabilizers with a V-tail, a design pioneered by the F-117 Nighthawk. This unique configuration allows the V-tail to serve a dual role, acting as both a rudder for yaw control and an elevator for pitch control. But how can two surfaces do the job of four? By actuating the V-tail surfaces in opposite directions, a horizontal resultant force is generated, providing yaw control, much like a traditional vertical rudder. Conversely, deflecting both surfaces in the same direction creates a vertical resultant force, providing pitch control similar to a horizontal elevator. This clever design is occasionally seen on unique aircraft, such as the Cirrus SF-50 private jet, allowing it to mount a tiny jet engine on top of its fuselage with the exhaust directed straight through the V-tail. That plane is so light it can even deploy a parachute to rescue itself in emergencies. However, for a high-performance fighter jet, linking rudder and elevator controls in a single mechanism isn't always ideal. Fighter jets like the F-35 and F-22 demand superior control authority, and that authority is directly proportional to the control surface area. Larger elevators mean greater pitch control, and larger rudders mean greater yaw control. If a single control surface is forced to perform a double role, needing both rudder and elevator action simultaneously, it inevitably reduces the overall control authority. This is why both the F-35 and F-22 feature large, distinct elevators, carefully offset and angled to prevent them from creating radar-reflecting corner reflections. But the trade-offs don't stop there, do they? What other design compromises are hidden in plain sight? Examining the engine air intakes reveals another critical area where stealth and performance clash. Both the F-117 and the B-2 have their engine air intakes mounted on the upper surface of the plane. This design cleverly prevents ground-based radar from bouncing around inside the intake and reflecting back to the receiver, and it also helps reduce the aircraft's infrared heat signature. However, for a plane like the F-35, which is expected to perform high angle of attack maneuvers in life-or-death combat, this simply isn't a viable design choice. Why would such a seemingly advantageous design be a problem for a fighter? During a high angle of attack maneuver, air intakes mounted on the upper surface would receive lower pressure, turbulent air. This drastically reduces engine performance precisely when maximum power and responsiveness are needed most. Conversely, air intakes located underneath the aircraft, like those on the F-16, would generate too much radar return. The solution for the F-35? Twin intakes positioned on either side of the fuselage. But these aren't just any intakes, they feature incredibly clever aerodynamic features, including a seemingly innocuous bump. This bump is a prime example of aeronautical engineering epitomized. Every seemingly insignificant design feature has a profound purpose. What exactly does this bump do to enhance both stealth and performance? Mounting engine intakes along the body of an aircraft presents a challenge that pylon-mounted engines avoid. As air flows along the fuselage, it forms a boundary layer of slow-moving, turbulent air. If this air is ingested by the engine, it not only degrades performance but can also cause severe damage. Imagine a turbine blade rotating through slow boundary air on one side and fast free-stream air on the other. The constantly changing force on the blade causes cyclical bending, a recipe for fatigue failure. Older designs, like the F-16, used a boundary layer diverter, a small gap separating the inlet from the fuselage, but this increased both radar cross-section and drag. The F-35, however, uses a diverterless supersonic inlet, or DSI. This ingenious bump creates a region of compression that pushes the boundary layer away from the inlet, simultaneously scattering incoming radar waves and lowering drag. The DSI, first tested on later F-16 variants, met all performance requirements and now graces the F-35, reducing weight by 30% and significantly lowering both production and maintenance costs. This single design feature embodies the F-35's philosophy of multi-purpose innovation, doesn't it? As we move down the plane, more hints of stealth design emerge. Long, sharp edges are the bane of stealth. They cause radar waves to scatter in all directions. What's more, radar waves can even travel along the length of a surface as a traveling wave and then scatter explosively upon reaching a trailing edge. To mitigate this, engineers employ a few clever techniques. The strength of that return signal depends on the length of the edge. So the first technique is serration, reducing the effective edge length by creating a jagged sawtooth pattern. You can see this very clearly on the trailing edges of the B-2 bomber, but on the F-35, it's far less obvious. Where exactly are these hidden serrations on the F-35? They're on every single unavoidable surface gap and access hatch across the aircraft. From the hatch that reveals a telescoping ladder for pilots to climb in and out, to the doors covering the landing gear, and most critically, the internal weapons bays. These bays are essential for keeping radar-reflecting missiles hidden from view. Even the smaller flare dispenser doors used to deploy decoys against heat-seeking missiles feature serrated edges. But flares do nothing against radar-guided missiles, which are becoming increasingly sophisticated. In response to this growing threat, a new, revolutionary decoy system was developed, deployed from a discrete panel on the F-35. What kind of technology can actively trick an incoming missile? When needed, this access door opens and a transmitter begins to reel out to a safe distance behind the plane on a fiber optic tow line. This system employs 3 levels of countermeasures to protect the F-35 from attack. First, it actively jams missiles as they attempt to lock onto their target, emitting precisely computed jamming signals through the fiber optic line. If the radar somehow manages to obtain a lock, the system then attempts to break that lock by disrupting the missile's tracking algorithms. Finally, if all else fails and a missile is bearing down on the aircraft, the emitter begins to simulate the F-35's radar signature, drawing the missile towards it as a decoy. These serrated hatches hide critical components, but even more can be done to reduce edge scattering in these locations. Have you ever noticed the subtly different color around these edges compared to the rest of the plane? That subtle color difference around the F-35's edges isn't just cosmetic, it's a testament to another ingenious stealth technique. These edges are treated with a special radar scattering tape. Just as traveling waves scatter when they encounter an edge discontinuity, they will also scatter when they pass over a change in electrical conductivity. The F-35 leverages this phenomenon to its advantage, causing radar waves to scatter over a longer distance, thereby reducing the strength of the return signal by spreading it out. This tape has a conductivity gradient, gradually decreasing its electrical conductivity. This forces radar waves to scatter at each interval, slowly decreasing the intensity of the surface wave before it reaches the physical edge, where it would have otherwise released one large, detectable return. It's like turning a single, bright flash into a series of faint, almost imperceptible flickers, isn't it? But the innovation doesn't stop at the edges. The entire surface of the F-35 is composed of specialized radar-absorbing material. In 2010, Lockheed Martin filed a patent for a carbon nanotube-infused composite material capable of absorbing radar waves across an incredibly wide range of frequencies, from 0.1 MHz all the way up to 60 GHz. This broad spectrum notably covers the frequencies used by advanced Russian surface-to-air missile systems like the S-400, offering the F-35 a critical advantage against some of the most sophisticated threats. The effect of traveling surface waves on stealth design can be seen in other surprising places too. You might imagine a cylinder would be an excellent way to scatter radar in all directions, but that's not always the case, is it? If a radar wave comes in tangentially to a cylinder, and its wavelength is at least 1/10 of the cylinder's circumference, the wave can actually travel around the outside of the cylinder and return straight back to the receiver. This phenomenon is likely why the F-35 features a sharp edge breaking up its otherwise circular nose cone. Where the F-16 has a nearly perfect circular nose, the F-35 sports a distinct ridge. However, the largest hatch on the plane is conspicuously not serrated, and for a very good reason. This hatch conceals the powerful lift fan, the heart of its vertical flight capability. The airflow in and out of this lift fan required incredibly careful consideration. The lift fan is essentially a miniature helicopter, generating 85 kilonewtons of vertical thrust, and in doing so, it creates a lower pressure zone above the plane, violently sucking air into the aircraft at a 90-degree angle. This air must travel smoothly over the hood to reach the inlet. Why would serrated edges, so crucial elsewhere, be a problem here? The hood covering the F-35B's lift fan must allow air to pass smoothly over it without creating excessive turbulent flow. Turbulent air would drastically reduce the performance of the lift fan, which is unacceptable for vertical flight. This is precisely why the inlet door is not serrated. Sharp edges, while great for radar scattering, would cause disruptive distortions in the airflow. This hood alone went through several design iterations to optimize the airflow. The demonstration X-35 aircraft, for instance, had two doors opening towards the side of the aircraft. This was later changed for the final F-35B in favor of a single, rear-hinged door. This design helps funnel air more efficiently into the engine and significantly improves pressure recovery, especially during short takeoffs where the F-35B doesn't take off vertically, but rather uses the lift fan and directional thrust from the rear nozzle to get airborne on extremely short runways. Watching this aircraft transform for vertical landing and short takeoffs is truly astounding, isn't it? It's the closest thing to a real-life transformer we've ever created. When the time comes to transition to vertical flight, a clutch linking the extended drive shaft of the F-35's main engine begins to transfer an incredible 29,000 horsepower to the bevel gear of the lift fan, spinning its contra-rotating blades. Simultaneously, gears within the rear exhaust nozzle begin to rotate. The mechanics of this nozzle are yet another wonder to behold. It's called the three-bearing swivel nozzle, composed of three airtight segments cut at specific angles relative to one another. By rotating these angled pieces separately and in conjunction, the nozzle can smoothly transition the engine's thrust downwards. While it's slightly easier to understand by visualizing individual segment rotation, in reality, all three pieces rotate together for a seamless transition. How does this complex mechanism allow for such precise thrust vectoring? Rotating the central piece alone can take the nozzle from a 0-degree turn to 45 degrees. This intermediate position is vital for short takeoffs where the engine's power is split between forward thrust and vertical lift. This short takeoff mode is just as impressive as vertical takeoffs, allowing the F-35B to operate from shorter, amphibious assault ships like the USS Mackinac Island, a vessel just 258 meters long. Its minimum takeoff distance shrinks even further with the aid of a ski jump ramp, often added to smaller assault ships. Watching the F-35 launch over such short distances is incredible. In these clips you can see the rear nozzle rapidly adjusting its angle of thrust in sync with the rear elevators, continuously fine-tuning the plane's pitch to ensure a safe and controlled takeoff. For a full vertical landing, the final nozzle segment can rotate to provide the complete 90-degree turn. It's a ballet of precision engineering, isn't it? The first nozzle segment can also rotate to move the nozzle side to side, but its primary function during transition is to ensure that the thrust doesn't move sideways as the nozzle changes angle. As we saw, if the segments rotated individually in a simple arc, the F-35 would spin wildly out of control. This intricate mechanism also allows the F-35 to smoothly transition from horizontal cruise to vertical flight and back again whenever needed. But the F-35 doesn't rely solely on the main engine and lift fan for this precarious balancing act. There are additional control mechanisms to ensure absolute stability. What other systems are at play to keep this marvel steady in the air? Bleed air from the main engine bypass is siphoned to two roll nozzles located on each wing. These nozzles provide thrust far away from the plane's center of pressure, offering precise control over roll during vertical flight. Additionally, there are guide vanes located underneath the lift fan. These vanes can adjust the outlet area to optimize the lift fan's performance, but they also have another crucial role: controlling the thrust of the lift fan from 5 degrees forward to 42 degrees backward. With sophisticated computer-assisted control of all these mechanisms, the F-35B is remarkably stable in hover compared to its predecessor, the AV-8B Harrier. This stability allows the F-35's single engine to precisely hover on 2 columns of air. But for a single engine to manage all this, it must be unbelievably powerful, right? Indeed. The F-35's engine, the F-135, developed from the F-119 engine of the F-22 Raptor, had to be incredibly powerful. The F-22 Raptor is a twin-engined fighter, giving it ample excess power for breathtaking maneuvers. The F-35, however, has only one engine and needs to squeeze out every ounce of power to perform a vertical landing. While the F-22's engine generates 156 kilonewtons of thrust, the F-35's can generate a staggering 191 kilonewtons. The F-35's engine boasts a much larger fan and bypass ducting, giving it twice the bypass ratio of its F-22 counterpart. This provides the F-35 with a more efficient engine for cruise flight and a much higher mass flow rate for greater thrust. However, this immense power comes with some drawbacks, doesn't it? While the F-35's engine is incredibly powerful, air that travels around the engine core completely bypasses the combustion chamber, meaning it doesn't get the acceleration generated there. This reduces the exhaust velocity, which in turn limits the plane's top speed. The F-35 has a maximum speed of Mach 1.6. While it's the first plane capable of both vertical and supersonic flight, the F-22 can reach Mach 2.2. The F-35 was optimized for loiter time, the ability to stay on station longer, rather than pure speed. However, all that extra weight required for vertical takeoff seriously compromises that ideal. How significant is the weight penalty for this vertical capability? The lift fan module alone weighs 1.2 tons, weight that serves no purpose in normal flight and demands more fuel to carry. To make matters worse, that critical space is used for an internal fuel tank in its non-B variants. Making the lift fan as light as humanly possible was absolutely paramount to making the F-35B viable on the battlefield. The fact that it only weighs 1.2 tons is astounding in itself. It contains 2 counter-rotating titanium blisks. What exactly is a blisk and why is it so revolutionary? A blisk means the blades and disc are all one single integrated piece, as opposed to the traditional method of creating a disc and attaching individual blades via dovetail connections. This innovative manufacturing technique significantly improves efficiency and eliminates a potential site of failure at the blade disc connection. This is an astounding feat of manufacturing, and the first stage fan takes it even further. Its blades are hollow to save even more weight. But where the F-35B truly comes into its own, where it redefines air combat, is in its modern suite of sensors and computers, all seamlessly feeding into one central display. That display isn't just any screen, it's the heads-up display incorporated directly into the pilot's helmet. Traditional heads-up displays like those found in the F-16 are integrated into a fixed panel in the cockpit. This means the pilot cannot see the display when scanning their environment, forcing them to constantly shift their gaze. In the heat of combat, situational awareness is everything, and the F-35's helmet does everything in its power to keep the pilot continuously informed. It even gives them what can only be described as X-ray vision and night vision. Information from a suite of sensors strategically placed around the plane feeds into a central computer, where it's processed and then displayed through a projector inside the helmet. Imagine being able to see through the floor of your jet to know what's below you, or through the wing to see what's approaching from the side. Inside a transparent faceted box underneath the aircraft lies a crucial part of this sensor suite. These aren't your typical windows, they're made from sapphire, a notoriously expensive gemstone. Sapphire is one of the few materials that is both incredibly hard and durable, yet transparent to an exceptionally broad range of electromagnetic wavelengths from ultraviolet to infrared. This allows the various sensors within to gather comprehensive data across the spectrum. However, the most important part of this entire electronic system is the radar antenna hidden inside the F-35's nose. This is an active electronically scanned array, or AESA, radar that operates very differently from traditional mechanical radars. How does an AESA radar with its hundreds of tiny antennas revolutionize detection and stealth? Phased array antennas have hundreds of tiny antennas. On the F-35's AESA antenna, you can clearly see metal plates set in rows, and each and every one of the slots cut into these plates is an individual antenna, 1,600 in total. This allows the phased array antenna to electronically steer its radar beams using the principles of constructive and destructive interference. If two antennas release two radar waves at the exact same time, with their peaks and troughs perfectly aligned, they result in constructive interference, significantly increasing the amplitude of the radio wave. Conversely, if the radio waves are set 180 degrees out of phase, matching peaks to troughs, it results in complete destructive interference, effectively cancelling out the wave entirely. This is the same principle used in noise-cancelling headphones. By precisely controlling the phase of each tiny antenna, the AESA can steer radio waves without any moving parts, preventing the radar from becoming a giant, directional beacon, leading enemies straight to it. Traditional phased array antennas are often passive, meaning every antenna in the array is driven by a single, central transmitter and receiver. This limits them to pointing in only one direction. If such a radar were tracking two enemy planes flying side by side and those planes suddenly split up, a passive phased array antenna would no longer be able to track both of them simultaneously. However, the F-35's phased array antenna is an active phased array. This means each and every one of its 1,600 individual antennas is its own independently driven transmitter and receiver. Imagine the power and flexibility this provides. This incredible capability means the F-35 can track multiple targets at once with zero moving parts, allowing it to maintain situational awareness across a vast battle space. The nose cones hiding these advanced antennas need to be transparent to radar waves, and as a result, they are usually made from glass fiber composites. This transparency, however, can cause issues for the plane's overall radar return signature, as an antenna like this will inherently reflect signals. This was a much bigger issue for older mechanical radar dishes, which constantly had to point directly at the enemy to track them, essentially broadcasting their position. The F-35's AESA, however, can electronically point its beams towards multiple targets while the physical antenna itself remains in a fixed position. This is why it is strategically pointed skywards to bounce incoming radar signals away towards space, minimizing its own radar cross-section. But how does the F-35 communicate without giving away its position? The phased array antenna also doubles as the plane's communication antenna, which is absolutely critical to the F-35's battle doctrine. The F-35 excels in the battlefield precisely because of its unparalleled networking abilities, constantly relaying information between its squadron mates and allied ground-based systems. This involves transferring a huge amount of data, requiring extremely high data transfer speeds. However, communication inherently comes with one glaring problem. It announces your presence to anyone listening. It is vital that stealth planes can communicate with each other securely without compromising their stealth, and the active phased array antenna facilitates this through its highly directional beams. It's like having a whisper that only your allies can hear, even in a crowded room. The F-35 utilizes the latest data link system called MADL, Multifunction Advanced Data Link, which significantly improves upon the experiences learned with the F-22's data link. MADL allows F-35s to quickly and securely share data from individual aircraft and ground-based systems. This torrent of information is then meticulously sorted, processed, and presented directly to the pilot in their helmet's heads-up display, right in front of their eyes. This gives them unparalleled situational awareness. There's no need to verbally communicate with wingmates if an adversary is underneath them. The planes automatically communicate and feed that data directly, into the helmet. The pilot can then simply look through the floor of their plane to see the exact location of the adversary themselves. Imagine the sheer tactical advantage of such instantaneous, intuitive information. This is the true strength of the F-35B. It is not just a stealth fighter, it is a networked hive mind capable of taking off from a ship a fraction of the size of an aircraft carrier and returning to it by hovering in the sky like a helicopter. It represents one of the most remarkable pieces of military technology ever created, a culmination of decades of aerospace innovation and a bold step into the future of air power. Its design is a symphony of compromises and ingenious solutions, all aimed at giving pilots an insurmountable advantage in combat. The F-35 has truly absorbed many lessons learned from iconic planes like the F-117 Nighthawk and the B-2 Spirit aircraft that once pushed the boundaries of what was thought possible. Like stories like this? Drop a comment below. Imagine a machine that defies gravity, disappears from radar screens, and fights with the collective intelligence of a hive mind. Sounds like science fiction, doesn't it? Yet this isn't a fantasy from a blockbuster movie. This is the F-35B Lightning II, arguably the most advanced aircraft ever conceived, a true marvel of modern engineering. It's a plane that promises to redefine air combat as we know it, blending the roles of multiple legendary aircraft into one incredible package. But how do you combine the agility of an F-16, the vertical prowess of an AV-8B Harrier, and the stealth of a B-2 bomber into a single airframe without making impossible sacrifices? The F-35B is designed to be a jack of all trades, a stealth fighter capable of engaging both airborne and ground targets with unparalleled precision. It's built upon decades of lessons learned from Lockheed Martin's previous ventures into stealth technology, drawing heavily from the revolutionary F-22 Raptor and the iconic F-117 Nighthawk. But the F-35B doesn't just incorporate these capabilities, it dramatically improves upon them. It's fitted with the most advanced sensors and computer systems imaginable, allowing it to share information almost instantly with allied forces, all while maintaining its elusive stealth. This real-time data is presented directly on a heads-up display integrated into the pilot's helmet visor, offering an almost superhuman level of situational awareness. Can you even begin to comprehend the tactical advantage of effectively seeing through your own aircraft? This incredible fusion of technology allows a flight of F-35s to operate as a single, coordinated entity, a true hive mind in the skies. But perhaps the boldest, most audacious capability of the F-35B is its ability to transition from horizontal to vertical flight with a simple push of a button. Utilizing directional thrust and a massive internal vertical turbofan engine, it can hover and land like a helicopter. This feature is not just a party trick, it means the F-35B can operate from the relatively small amphibious assault ships of the US Marines, extending its reach and tactical flexibility exponentially. But how do engineers manage to cram all this cutting-edge technology and such conflicting requirements into a single, cohesive airframe without compromising performance?